Great presentation. Thanks so much, Phil. Really excited about the Exodus phone. I'm sure many people here are as well. All right. Up next, we have a very exciting presentation and a demo that I think everyone here should be excited to see and blown away by. I'm sure many of you here know who Gavin Wood is. He's, of course, the co-founder of Ethereum and the mastermind behind the Ethereum yellow paper and much that went into the Ethereum design. And for the past couple of years, he's shifted his focus to building the next generation of Web3 technology in the form of the Polkadot protocol and the substrate technology, which makes it easier than ever before to build and deploy your own blockchain. So I think we're going to see a demo of that today by Gavin. So Gavin is the co-founder of Parity Technologies, president of the Web3 Foundation. Do we have a green light? Is Gavin ready to do this? All right. Oh, sorry, there he is. All right, take it away.
Who was at EdCon in April this year? Hands up. Anyone? Oh, not very many. A few. Well, at EdCon, sorry, I did a live demo of a substrate-based chain being bricked by a runtime upgrade, by basically a sort of upgrade to its internal mechanism. Not wanting to be outdone by myself, I'm going to ratchet things up a couple of notches this time. I have here, fresh from the Apple Store, a shrink-wrapped MacBook Pro. And I hope over the course of this hour, I'm going to give you a demo of developing a custom blockchain and upgrading it online using this very computer. I would like a volunteer from the audience to help me, please. You don't need to know very much, but if you have been through the Apple setup procedure before, that would probably be helpful. You get a T-shirt if you complete successfully. Yeah, go on, you're closest. What's your name?
Victor.
Say again?
Victor.
Victor, round of applause. Okay, feel free to undo the shrink wrapping. Right, and yeah, let me know when you're good to go. There is a set of instructions that I compiled for you. UK, British keyboard. There's the Wi-Fi password. If you can't read the slightly messy handwriting, then Tomek here will be only too pleased to help you. We don't want to transfer any files to it. Yeah, create the account, Gavin, the password is password. Let me know when you have a terminal. Hopefully we can connect this to the HDMI. Is that right? Yeah, that looks about right. And the audience can see, at least on one of the screens, how things are going. Cool. Right, the talk. So this is basically split into two sections. The first 30 minutes is me telling you about Substrate and Polkadot, and the second half hour is hopefully, if Victor can complete his duties, a demo. So I think there's some confusion over what Substrate is and how it relates to Polkadot. And this talk is sort of meant to clear up some of that confusion. Is this side of the hall okay looking at the installation procedure? Or are you desperate to... Yeah, good. Okay, good. At the back, I can't get the right-hand screen. That's gone blank. It would be very helpful if you could make it not blank anymore. Yeah? We good? So how do they relate to each other? Cheers. Basically, Polkadot is, in many respects, the biggest bet in this ecosystem against chain maximalism. I don't like chain maximalism in general. I consider it a sort of nationalist equivalent of blockchain. And if I can do something helpful for this ecosystem, I would try to convince people that it's really not such a good plan to be so focused on making, on backing one winner above all others. I don't think, even if there were one perfect chain, I don't think it would stay perfect for very long, and I don't think it would be helpful in general for people to try and buttress it. I consider this kind of maximalism basically just barriers to entry, and barriers to entry generally reduce innovation, and they reduce the fun for technologists like me, and I hope for like you too. So, how do they relate to each other? Well, these are separate technologies. They're designed to work together, but really it's more of an optimization that they work together. It's not something fundamental about their design. If you want to think about it in sort of analogies, you can think of Polkadot being more like the Ethernet protocol, and Substrate being more like the sort of general IBM PC or Mac or whatever that uses the Ethernet protocol in order to sort of communicate between themselves. Polkadot is a specific protocol. It's a token. There's a token associated with it that lets you pay for using that protocol. It's got many teams, at least a couple of teams at the moment, and hopefully many more, and multiple implementations. Substrate, on the other hand, is a technology stack. It's created originally by Parity Technologies, although being open source, I hope that we can sort of attract other people to contribute. We already have a few sort of external community contributors. I hope we can get many more over the coming years. And the idea with Substrate is that it's not used for any single network. It's used for many different chains, many different tokens, and in principle could also be re-implemented in other languages. So you can see it's sort of a Venn diagram. On the one hand, you've got like Polkadot and the parachains of Polkadot. They don't need to be written on a Substrate stack, but they can be. We'll make it easy for you to do that, but hopefully there will be other technologies that come along and that allow you to make Polkadot chains without using Substrate. And similarly for Substrate, the chains that you build with Substrate don't need to be used with Polkadot. We make it easy for them to be used with Polkadot, but in principle, they can exist perfectly well on their own. This is a somewhat complex schematic. I don't expect you to understand all of it, but the basic point is that in both the Polkadot protocol and in the Substrate model, you have this notion of a embedded runtime or block validation function in the case of Polkadot. And this is meant to be relatively analogous code. They do more or less the same thing. And because of this, we can start to see the sort of the analogous components between both Polkadot and Substrate. So, to give an example, both Polkadot and the sort of parachains need both an RPC, they both need database, they both need synchronization algorithms, they both have a WebAssembly execution engine. These are like common components. Why should we be building them twice, once for parachains and once for the relay chain? Doesn't make any sense. So if we go to the model of Polkadot sort of version 1, and this is the thing that I basically laid out in the Polkadot paper, whatever it was, 2 and a bit years ago. The basic idea is that you have the consensus algorithm at the very bottom. That's whatever it is that's making sure that the chains don't fork off away from each other. You've got the Polkadot runtime environment, which is the thing that sort of actually looks after execution of the block, that sort of knows how to run the transactions, that sort of thing. Then you've got the relay chains runtime. That's the thing that actually describes what Polkadot is, how it works to the runtime environment. Then you've got the things that run sort of within the runtime, like the parachain consensus, making sure that the parachains are all correctly operating, that they're valid, and so forth. And that's sort of on the relay chain side of things. And on the parachain side of things, you've got the authoring and the synchronization mechanisms to actually bring forth the new blocks for the parachain to keep getting bigger. And that runs within the parachain, that runs the parachain runtime environment, and then the actual parachain runtime is the thing that decides what it is at the parachain, how it works, how it executes transactions, what the transactions mean, and how it executes blocks. If we go to the version 2 model of Polkadot, then we see, if we go back a couple of slides, we're going to merge the parachain runtime and the Polkadot relay chain runtime into the same bit of code. And when they become the same bit of code, or more importantly, when all of the components around it can interpret them in the same way, then we can put a feedback loop between the parachain runtime and the relay chain runtime. And that feedback loop is super important. It has a very particular thing that it achieves, and it relates specifically to scalability. So if we look at the version 1 of Polkadot, we say how many parachains can Polkadot reasonably handle? It's something along the lines of probably dozens, perhaps 100. If we go to version 2 of Polkadot, where the relay chains can be pluralistic, where each of the parachains can itself be a relay chain, then we can introduce multiple levels of Polkadot. And we end up with something approaching this. So we might have sort of the main relay chain at the top there, but on the first level, there could be other relay chains, copies of that relay chain, or in terms of its operation. And those relay chains can then host their own, however many, 100 or whatever, parachains. Some of those parachains might be relay chains as well. Others might be interesting state transition function chains, like maybe a plasma parachain, maybe a ETHEREUM 2 Shasper parachain, maybe a ZK Snarks-based parachain. Who knows? It may be that you get to the bottom and you have a relay chain that's just full of parachains that are all for one specific consortium. So maybe something like an EWF set of chains that all basically run in a zone together. Now, in building Polkadot and in building Substrate, we realize that we will fail in our mission of building a platform that is inclusive if we accidentally come into competition with other next-generation chains. We don't want that to happen. And I believe that the difference between competition and cooperation is pretty much based in the technology, and specifically based in the neutrality and freedom that you get from working on a platform. If a platform gives you the freedom to do what you would do otherwise, but yet some additional advantages, perhaps speedier development, then you're more likely to use it. So we're designing Substrate to have the maximum level of technical freedom, and you also get security and connectivity built in for free, with minimum efforts and constraints, and for that matter, the opinionation that can creep in if you're not careful when you design these platforms. So I want to try and convince you that Substrate really is a sort of general platform for building your next blockchain on. So why why do I think this is a really general platform? Well, firstly, minor things like the block format. We have an abstract block format. As long as your block format sort of encodes the 2 or 3 or 4 specific values, things like parent hash, then you're good. You can put whatever else in that you want. It's extensible. It's agnostic to the underlying crypto databases. You can choose our very Ethereum-like Merkle Patricia tree. You can have any of the other crypto databases that we write for the various parachains that we want to make. You can introduce your own. That's perfectly fine. And you can organize these dynamically in any way that you want. If you want to have hierarchical trees, then you're perfectly at liberty to do that. It's got an execute block function. Now, in general, blockchains have an execute block function. That's one of the sort of notable constants of blockchains. And we provide a 100% abstract execute block function. You give it data, like a block, and it executes it. It's encoded in WebAssembly, which can be targeted from any one of a number of languages, including C++ and Rust. And I don't think it could be possible to make a more general execute block API. But if you have ideas, let me know. It also has extensible networking and extensible CLI and RPC. So if you want to put in interesting things for managing your networking, maybe managing peer sets, maybe introducing new CLI options, introducing new RPC calls, it's all good. So what about consensus? Well, we also have that generalized as well. There's an API provided. You can sort of roll your own consensus mechanism if you want. We've taken quite a lot of time and iteration to make sure that this API can handle probably most interesting consensus algorithms out there. We also provide a few of our own. Rhododendron, which is our blockchain context of PBFT, is in there. Orand, which you might have heard of if you've been using Kovan, or any of the sort of parity POA tools, is a probabilistic finality consensus algorithm. We have a, well, actually, this is where I come to an interesting point. We actually have an algorithm that has 2 names. Its implementer gave it one, and its designer gave it, with my help, another. And it would be good if we could come to an agreement over which name it should ultimately take. So I think that the shared ancestry finality tool is a decent enough name for it. Is Rob here? What does grandpa stand for? Or Al? No? Okay. It's something to do with ghosts, something. I don't know. I don't think it sounds as good. Personally, I think we also have a few others that we are planning to implement. Ouroboros proof of work. It's generic enough to bring in the proof of work consensus. And obviously, the ultimate goal for this is to have a parachain consensus whereby any substrate chain that you write can be turned into a parachain. So if I've convinced you it's general, then now I need to convince you of its advantages. So what do you get? Well, you get hot swappable pluggable consensus. Yep, you can change your consensus mechanism on the fly. So if you want to start it with Orand, and then you want to add finality down the line with shaft, that's perfectly fine. You want to switch it from that to become a parachain? Well, we want to make that work as well. It's got a hot upgradable pluggable state transition function. What do I mean by hot upgradable? Well, I mean that you can launch your chain, and then down the line, you can change what it is that your chain does, how it works. It's very internals, without a hard fork. It's got a light client. You just get a light client for free. You want to use it on mobile? You're good. It can work. You get chain synchronization, pub sub RPC, transaction queues, all that sort of general stuff, pervasive and secure networking by virtue of the libp2p protocol. You get a JavaScript implementation, if you like JavaScript, and you get our runtime module library, which lets you take from our library of, I think there's about a dozen modules now, and that's growing all the time, in order to build your perfect runtime. And, of course, you get interchain connectivity by virtue of the Polkadot protocol. So the SRML, which is our runtime module library, and as I say, this is the way that you can sort of take off-the-shelf components, plug them together, and build yourself a blockchain that does what you want it to do. We have a bunch of components already made. The idea is to get each of these audited in turn so that they can be used as common building blocks. And they can have UI sort of analogs as well, so that you can plug in common JavaScript components in order to make really easy, rapid developed applications. You've got things like accounts and balances, so that you can actually use, you can make a cryptocurrency. Who'd have thought that was one of the many use cases. You can use sessions. There's a staking algorithm, so you can use proof of stake. So the way that Substrate works is the consensus algorithms generally just provide a proof of authority, and then you can, by switching out which authorities are looking after the chain, you can turn that into a proof of stake mechanism. We'll probably have a couple of those by the time we get to 1.0. It's got things like treasuries, which is a little bit like the DAO. It's got smart contract module, so if you want to put smart contracts in there, you just include that. It's got various things to do with on-chain governance. At the moment, we have a couple modules for referendums and managing a sort of delegated council. You want to add arbitrary fungible assets, we've got a module for that as well. But as I said, these things are being constantly developed, and we want to turn this into a very reasonably large library. So the problem is that when you're sort of coming up with these platforms, these APIs and protocols, you end up with a kind of a trade-off. On the one end, you've got like minimum effort. Like, I want everything just done for me. I can just like configure it with a JSON file and like choose which bits I want, and that's it, right? All sorted. And then on the other hand, you also want to provide maximum freedom, which is like, well, I really want to do X, Y, and Z, and maybe you didn't think of that when you designed the protocol or you designed the API, so how is it that I can do that? And really, we want to get both. And the way to get both, at least that we're using, is to have a multi-layered architecture. So at the top level, there is where you've got like the maximum amount of freedom, but also the maximum amount of effort that you have to put in. And that's for stuff, basically you start with Substrate core, right? And that gives you a bunch of stuff, but it makes your life of building a blockchain a lot easier than it would be if you started from scratch. But you don't get anything really finally made for you. In the middle there, you've got the runtime module library, so that basically means that you can use core, add the runtime modules to it, and you end up with something that's much easier to get something working, and still has a decent amount of freedom. You can make your own runtime modules if you want, you can hack at the code if you want, that's fine, but it is more opinionated, so you have to fall in with the architectural decisions that we made in that library. And finally, there's Node, which is our sort of maximum ease, maximum opinionation. And with that, that's basically kind of on a similar level to the parity Ethereum client. It's, you configure it with a JSON file. it kind of does what you expect. It deploys a blockchain pretty easily. For today, in the demo, I'm going to go for the middle layer. So I'm actually going to do some live coding in front of you and show you how to make one of these runtime module libraries. So going over it, if you have the bare Polkadot sort of parachain, then it's kind of, you give a block validation function, which has to be in WebAssembly, and you give it some collator nodes, which basically provide these candidate blocks, and you have to do everything. You have to do RPCs, databases, syncing, all of that stuff. If you use Substrate Core, then you still have to provide this execute block function written in basically WASM. You can write it in Rust or C++, whatever you want, but you still have to sort of write it all yourself. And you also have to provide any networking block authoring stuff if what we give you isn't sufficient. And you get a bunch of you get a bunch of stuff. You get RPCs, databases, you get telemetry, you get the light client, pluggable consensus, upgradability, and a bunch of other things. If you go for the runtime module library, then you get a bunch of modules. Well, you get a bunch of modules to select from, but you have to select them, you have to configure them, give them parameters, and you get a load of front-end help. You get block authoring and transaction queue. You get the ability to have a JSON configuration file automatically made for you that just works with your eventual executable. You get a chain explorer that will work with all of your runtime modules. You get event tracking, which I'll probably touch on in the workshop if you come to that later. Finally, if you just use our node, then you provide a JSON config file, and you get a blockchain. So with regards to Polkadot, there are basically, well, Polkadot and Substrate, there are basically three options that you get. You get a solo chain and a bridge, or a parachain. They're at differing levels of sovereignty and connectedness. Solo chain is self-sovereign, it doesn't connect to anything else, it just lives on its own. Solo chain, if you add a bridge to it, basically the bridge is a module that the solo chain listens to and can also listen to Polkadot, and basically provides that kind of intercommunication between the two. It retains its sovereignty, and it's up to the bridge to basically explain to Polkadot what that sovereignty means. Problem with it, of course, is that you don't get the security that Polkadot would otherwise offer. Finally, as a parachain, you get to use the relay chain's consensus, or any of whichever one that you put it on, if it's not the top-level relay chain, and it uses the validation for that. You don't need to incentivize your users economically. That job's already done because you're piggybacking on the relay chain's consensus. And it's sovereign over state transition still, it's just not sovereign over finality. So I want to very quickly talk about parachain set governance for Polkadot, since that seems to be something that people are sort of quite interested in knowing. Version 1 of Polkadot probably hosts several dozen parachains, perhaps, as I say, perhaps up to 100. So that's limited capacity. 10 or 20 slots will be reserved for some of the future chains, leaving perhaps 80. And they'll be leased, right? So it's not a sale, it's a lease. You put in some dots, and you get the dots back when the lease is over. And the idea is that there's a quadratic curve, it's a polynomial curve, and it goes up as fewer parachain slots become free. And parachains can be added through edict of referendum, so you can just have a referendum to say, yep, we the people believe this parachain, or we the coin holders believe this parachain should be introduced. Or you can take up one of those slots by putting down dot tokens, and you specify a desired lease period. Once the leases can be exchanged, so if you're coming to the end of your period and some of the chain still has quite a long way to go, you can sort of have an arrangement whereby you take their lease off them. And once it's ended, the chain is retired. If all of the slots are leased, then it goes into an auction. If they're not, then it just gets added back onto the end, back into the free slots, and the effective price for taking a parachain goes down. So The roadmap, we're kind of at a few days off POC 3, and yeah, so Substrate's going to have a 1.0 beta release. Just once we've integrated our new consensus, our shaft consensus, and that will be called the 1.0 beta, and that should come out over the course of the next 3 weeks. POC 4 is scheduled for sometime between January and February next year, and that will include interchain communication. And that we are also planning on making the 1.0 release candidate for Substrate, with the 1.0 candidate following basically after the key components have been audited. Things get a little bit kind of more difficult to predict the future, a bit more vague, but basically POC 5 should see something of a bringing together of Polkadot parachain collator software and the Substrate software. So basically, Substrate can start to be the collator nodes. It can start to offer parachain consensus. While that's going on, we'll be working on the things like the Ethereum bridge and a few other infrastructure components, with our hopeful date for a 1.0 release candidate to be the beginning of July next year, and still on for a Genesis block at some point between September and October. So yeah, get Substrate and launch your chain. Are we nearly done there? Oh dear, we're not. So it turns out that the Funkhouse's internet connection is not super awesome. How close are we? Yeah. Okay, we're just downloading Substrate, and it seems to be going at about 0.1%. No, 0.01% every 10 seconds. Who will be using parachains? So yeah, okay, so let me take a few questions while this is downloading at snail speed. Oh, okay, no, it's speeding up now. So I'll take a few questions anyway. So if anyone has questions over the topics I've brought up in the talk so far, let me know. Yep. So how would I imagine a future with Polkadot, presumably, and
Polkadot or competing chains. You envision a lot of different protocols all working together.
Yeah, I mean, I kind of look at it like the original sort of Ethereum vision was, lots of different smart contracts all working under the same Ethereum umbrella. I don't think smart contracts are the only, and perhaps not even the best, abstraction method for describing the sorts of things you want to do under the roof of a consensus system. They perform certain duties quite well, particularly when the code is small and you need lots of small components to actually talk to each other, generally synchronously. They don't work so well in pretty much any other circumstance. And therefore, I see quite a lot of use cases of consensus systems, consensus, yeah, whatever you can use consensus stuff for, to come under the roof of a broader and lower level abstraction model with the basic kind of, here are the types of transactions that this system can accept, pretty much in the same sense that a contract has an API, and you specify the entry points as methods on that. I kind of see that, but at the level of a blockchain itself. So if you want to kind of think of it in Ethereum terms, then Ethereum has basically transactions can do two things. They can send balance and potentially end up executing some code, or they can create a contract, right? And those are two very different sort of paths of execution that a transaction can take. I don't see why there should be, if there's two, I don't see why there shouldn't be any number of such paths, and they can be introduced. They should be able to be introduced and upgraded programmatically over the course of the chain's lifetime. The alternative, of course, is just to have a single sort of transaction type. And that's also fine, but I look at that as being a different model and not necessarily one that's much better, because ultimately, unless it is a single function, like a fixed function blockchain, then it's unlikely to end there, and at some level, somewhere, they are going to get, there will be a condition, and they'll get forked out to different paths. So no, I don't really see the difference between different chains and different contracts. I just see a difference in abstraction level. Any other questions? Yeah.
Currently, when I use different chains, I have to use a different tool set. So do you see me using the same tool set across all these parachains?
So do I see there being different tool sets across different parachains? I see a lot of shared tooling between the parachains. The SRML is one example of that, where if you build parachains using the substrate model with SRML, then you're likely to have a huge amount of shared tooling, blockchain explorers for one, UI components for another. And that's one of the trade-offs that you come to. If you want to kind of do a greenfield job and start from scratch, that's fine, but then you're probably going to end up having to write your own tooling from scratch. I see things like larger components like the smart contract, like the WebAssembly smart contract component that we built for SRML, being something that sort of gets used in almost every chain that wants smart contracts at all. And I see smaller runtime modules, like, for example, our assets module, as something that's sort of partly throwaway and probably wouldn't have so much tooling surrounding it. But yeah, in general, I would say that I would hope at least that there are multiple teams developing multiple sets of tools and multiple sort of parachain software stacks in this environment. And even if it's not specific to Polkadot, even if it's other blockchain technology stacks, I would hope at least that there is eventual sort of tooling that allows bridges to be built and higher level things not to have to worry about that as well.
So when I publish a smart contract in Ethereum, yes, I can expect that this will last forever, but maybe not, because why would my code bloat the full node of everybody that's using it? Mm-hmm. But still, this was a supposition, but now there is talk of changing this a little bit, so you also lease the state or the storage of smart contracts. But here, this is built in, so you have to take more care later if you want to see your code running forever, What's the point here?
That's true. So yeah, so the point is that if you introduce leases for applications, then the application may not last forever. It's kind of romantic, this idea of an application, and once you deploy it, it's like it will stay there forever. But as with most things that are romantic, when you come to the actual practicalities of it, it often doesn't stand up to scrutiny. In the case of the ever-bloating blockchain, because once you deploy a contract and pay once, the contract sits around using up that bloat indefinitely, yeah, that's problematic. So with leasing, at least, as long as you're willing to, I mean, the price of a lease will go up, but in principle, you can get like 5, and who knows, with other relay chains, like lower down in the stack, they may offer like really long leases, like 50 years, 100 years, and at that point, maybe it's approaching forever that it doesn't really matter. There are other ideas that we're sort of thinking of implementing on our smart contract, within our smart contract module, that sort of increase the ability for you to be sure that your smart contract will be around at least as long as the chain, even if it's deploying quite a lot of storage. And that basically comes down to a sort of rent payment that once the rent payment runs out, rather than the contract being destroyed, simply a hash of the storage is left, and it's up to you to, if you want to sort of trace the chain and sort of do an archive node, you're able to restore the contract in all of its state with a sufficient payment. So, yeah, there are sort of ways to address this, but in general, this pay once, it sits there bloating everyone's hard disks up forever is probably not going to work.
Can you compare Polkadot to Plasma and talk a little bit more about bridges and how security is achieved in bridges, like how security of fund transfer is achieved? For example, can I move half of Ether supply onto some Polkadot parachain?
Sure. I mean, we can get quite deep into the bridges. Basically speaking, bridges work by having a light client on both sides of the bridge. And the light client interprets whatever state transitions have happened and introduces them as sort of, we call in Substrate extrinsics, but you can more or less think of them as transactions into the other side of the bridge. And this lets the other side sort of interpret what's going on. The security guarantees that you get are roughly analogous to the security guarantees you'd have with a light client. The biggest issue with bridges is where you're bridging a chain with finality, with absolute finality, to a chain that has less of a finality guarantee or less of a security guarantee on it. And in those cases, it basically comes down to probabilistic. You hold out for however many blocks you decide is enough to be probably fine, and then shovel the data across. Plasma. Yeah, so there are sort of huge differences in architecture between Plasma and Polkadot. It's probably probably better for me to answer that question more in person, but sort of outside of this context. But the rough idea is that Plasma is very much more geared to transient fixed function chains, and Polkadot's really about arbitrary function and permanent chains, and they're very much sort of geared to their own particular niche. But because Polkadot is arbitrary function, it makes the parachain model quite an effective model for implementing something like the Plasma protocol. I would say more so than the smart contract model in Ethereum, but time will just have to tell on that one, and yeah, hopefully we'll see.
If you want to build an application that has the interoperability property, and you can choose to build your own parachain or a smart contract, right? So would you go into the trade-offs when to choose one or the other?
Yeah, so if you find yourself worrying about gas limits, then probably that's an indication you should be moving to a parachain. If you find yourself worrying about how to possibly interact with some other smart contract that you know is deployed, a name registry or something, then maybe it's better to move on to the smart contract model. It really comes down to, it's kind of like, should I write my application in JavaScript or in Rust? It's like they're very particular tools for particular domains, contexts. Usually it's pretty obvious. Like once you start writing the thing, it becomes pretty obvious that, yeah, I should probably be writing it with this tool rather than with that tool. The specific trade-offs between smart contracts and runtime modules, like or parachains. I mean, I look at runtime modules as being kind of halfway between smart contracts and parachains, because they offer you quite a lot of the advantages of smart contracts without, while still being essentially the sort of lion's share of all of the advantages of having a whole parachain. And in essence, the main differences are runtime modules are, or parachains, are not limited by compute. So you only have to put forward a block that the validator basically waves through. You don't have to worry about things like gas metering and storage and whatnot. That's up to you to ensure sort of isn't gameable.
The runtime governance, the governance, the upgradability applies to the runtime and not to the smart contracts.
The upgradability applies to the chain as a whole, the whole parachain. So if you want to upgrade a single runtime module, that's fine. You just build a new parachain that has that upgraded runtime module and deploy that. Similarly, can be added and removed. You can change it entirely. You could literally rewrite your parachain from scratch in C++ and deploy that as an upgrade. There's no, as long as you have a WebAssembly blob to put into place, then it all just works. With a smart contract, I mean, runtime upgrades to smart contracts should be easier than upgrades to whole blockchains. It's just that the tooling isn't there yet between languages and potentially execution environment to make it super secure. But yeah, I have no doubt that within a year or two, there will be compelling ways to upgrade smart contracts. Okay, how is this?
This is building node template. This is installing substrate, and the rest is done. So we have cloned the repo, visuals repo. Should be ready to go. It
Okay.
just, it didn't compile the whole thing.
Okay. Okay, so we've probably got time for one.
Right here, right here. You're back.
Over here, behind you. Question about composability. An emerging trend in 2018 in the Ethereum ecosystem has been people using smart contracts of others as building blocks. So just a concrete example, at ETHSF hackathon, someone used Augur to build the synthetic derivative of the S&P 500 price. It was hedged with short Ether by DYDX, and that was wrapped into set protocol under the hood that was traded with 0x, and then DYDX, short Ether uses DAI under the hood. So it's kind of really interesting how developers can, instead of building smart contracts from scratch, kind of to the bare metal, they can just compose all these smart contracts. And I think we'll see much, much more of that. What are the implications of the parachain model on composability, where things can't be atomically executed in the same VM?
Yeah, so I mean, one of the wonderful things about the smart contract model is indeed the ability to interact with others in a synchronous manner, so relatively thought-free manner in the same environment. And if that's the model that your application sort of requires, then probably that's going to be the thing that you need to use. With parachains, there is a obviously intercommunication between the parachains is something that's been explicitly built in from scratch, but it is asynchronous, which means the tooling will take a while before it gets to the point of being anywhere near as easy as it would be in a smart contract environment. I do think composability is super important. I think that these lower level components will require substantial middleware before composability becomes so easy. I think smart contracts will stick around as a means of very quickly prototyping and deploying particular ideas. But I think once you push those ideas out to once they become popular, once you need to really increase throughput, then you're probably going to kind of optimize in basically the same way that when you've got an FPGA circuit that does the trick, you optimize it by sending it to a fab and having an IC printed, 10,000x. I suspect it will be the same with this. You kind of you innovate very quickly with within the smart contract environment, and then when you're happy with your application, you roll out a sort of parachain that takes that smart contract or a set of smart contracts and deploys it in a way that's almost certainly going to be much more efficient, partly just because you don't have to worry about gas metering. I do think that long term, we can probably get the middleware to the point that parachains will not be significantly harder to compose than smart contracts. But I think we're looking at like 2 years maybe before it's like, maybe even 3, 4, before it's built into the language, before we have things like async helpers, so you can basically just write linear code and it automatically uses stack pushing in order to save its state and come back once the message is returned. So yeah, it's going to take time before we get to that because it's just a lower level environment to play with, but I think it will happen. How are we looking? Okay, we're getting there. This is one of the last few modules. Any other questions?
Very impressive, thank you, Gavin. For simpletons like myself, what's the wider implication of this? What out there in the teams behind Ethereum, etc., this means that developers won't have to wait for the team at Ethereum to implement tools for them? Is this radically transformative for developers? How fast do you think this is going to speed up the whole ecosystem?
Well, I mean, I'm hoping very fast indeed is the answer to that one. I mean, this is designed to be all of our lessons learned in building Ethereum, all of our efforts in making Polkadot as good as it can be. We're trying to distill down into a single, a stack of tooling that allows you to get all of those same rewards with near zero cost in terms of time, in terms of money, just in general. You get all of that for free. How well this works is going to be to some degree, a judgment on our ability to provide a product that works, and I hope we can really come through on that. But it's my hope that when we push out Substrate 1.0, this will be a sort of a turning point that makes the idea of a multi-chain or a polychain world a sort of a captivating one. At the moment, when you want to develop new functionality, you write a smart contract, and if you think you've got what it takes to develop a sort of low-level technology, you go the whole hog and you write a whole new blockchain, and that takes a very, very, very long time and a lot of skill. I really hope that by pushing out Substrate, we can create a whole new class of sort of development teams and development applications that sit right in the sweet spot between the two, where you don't have to know everything, you don't have to do everything to develop your whole new blockchain, but you can do just enough that you do have a domain-specific chain that has its own parameterization and its own features that allow you to get a particular job done and done well that wouldn't have been possible before because smart contracts are too bloaty and writing your own chain is too much work. Alrighty, it seems that we are ready. Slow. I have 15 minutes left, it seems. So let's see what I can do in 15 minutes. Right, the first thing I'm going to do is launch a blockchain. Hopefully this is... did you compile the WASM first? Yeah, okay, cool. So what we're going to do is target release node. So node is I'll explain to you what's just happened actually first. So this is a new Mac. It's had Rust installed on it. It's also had npm node installed on it. We've downloaded and built what I've a package called the repository, I should say, called the substrate node template. What this is a very small repository that acts as a sort of skeleton blockchain. I can take you through all the code. Can everyone see both? Yeah, we're going to both. Good. So this is the whole package. As you can see, source. There's a main RS. It's got a bunch of boilerplate that just handles when you press Control-C. And it's got a bunch of information on the version. In this case, we're setting the executable name, node, the author, anonymous, and the description. This code is under the unlicense, so you can take this and you can do whatever you want with it, right? This isn't, we're not even trying to like GPL this. This is just out there, public domain. Then we have the CLI, which is basically the thing that does the sort of nuts and bolts. In the CLI, we have a bunch of imports. We specify a couple of chain specifications. So chain specifications, if you've used parity before, these are kind of like the difference between running a dev chain, running a local testnet or whatever, running the Ethereum mainnet, running the Ethereum Classic, running Ropsten. All of those different kind of specifications, they're chain specifications. This one comes with a development specification, which is just a single kind of authority behind it, and it's got a local testnet as well that has 2 authorities behind it. And we can see these being configured down at the bottom. This just prints some information about it using the parameters from the main. If we go into chain spec, we can see those 2 chains. There's the testnet genesis. So this is the thing that sort of I was mentioning before, that if you use the SRML, you get this kind of genesis configuration thing. You can configure the genesis. So here's the block period, 5 seconds in our case. The consensus module gets given a bunch of authorities. We're going to parameterize these because they're different for the development and for the local testnet. The balances lets you set things like the fees for transferring and the initial account balances. We also got this upgrade key module, which I coded very swiftly for this particular demo. The upgrade key module is you give it a key, and anyone who can sign a transaction with that key can upgrade the blockchain. Okay, so it's super, super duper simple governance. The development config basically just gives Alice, Bob, Charlie, Dave, even 30 a bunch of tokens, and it also provides Alice as the single authority on the network, able to produce blocks. It also names Alice as the upgrade key person. You can see those 3 parameters are passed into testnet genesis. That's all it does, very simple. That doesn't really have anything in it. That doesn't really have anything in it. This sets up this does all the nuts and bolts of actually setting up the blockchain. And if you want to parameterize stuff like the transaction queue or the networking, then this is where you put your parameterizations in. This is basically just default. The only other code left is the runtime. And the runtime is the thing that actually describes what the transactions do, how the blockchain works. I'll take you through this. All this stuff is just bringing in things from the external environment. It's not very interesting. We have an account ID, which is an H256, a 256-bit quantity, which is actually just an ED 25519 public key. We're using the ED 25519 crypto for this chain. Our hash is again just a standard hash, and that's 256-bit quantity. We're using a U64, 64-bit integer for the block number, and for the transaction index or nonce. We need some opaque types. This basically defines how much we can upgrade the chain as to how opaque these types are. These are very opaque types as it happens, and therefore we can upgrade the chain basically all we want. We also have some version information for the runtime. In this case, template node is the specification name, and substrate template node is the implementation name. The idea is that by splitting up the specification and the implementation, we can say that other people can make new implementations of the thing that's meant to be the same specification. And they each have a version index attached. Finally, we're into actually parameterizing the individual runtime modules. So for the system module, which contains all of the basic stuff to do with blockchains, things like account ID, block number, the hashing algorithm. So for hashing, we're using Blake 256. We've got all of this, all of these types. Then we can go on and parameterize each module independently. We have a consensus module, and we parameterize what happens when a validator is offline. In our case, nothing happens when a validator is offline, but in principle, we can set up some sort of punishment mechanism for that. I've got a timestamp module. Timestamps don't come as standard with Substrate. You have a module for that. Like, we keep Substrate as minimal as possible. Balances, this allows us to have a cryptocurrency on the chain. In our case, we're using the type for a balance as a 128-bit integer. Thank you, Rust guys, for finally implementing that. We have a 32-bit account index. That's basically how many accounts we can enumerate, so 4 billion or so. And if you go above 4 billion accounts, then things will start to break, so make sure that that's a sufficiently large data type for that. We can do we've got a bunch of hooks for what happens in certain instances. And the upgrade key just requires, it uses an event mechanism, so it requires the ubiquitous event type. We can construct the runtime. We just basically list all of these modules here, along with if they don't implement the default things, we have to specify what things they do implement. And these are our eventual types that we can create from our runtime. Notably, we specify ED25519 crypto for our transaction checking. Beyond that, we've got a bunch of very simple proxy functions that basically implement our API endpoints. The only ones you technically have to implement are these three. You have to tell the sort of harness of Substrate, the client, what version you are, what the authorities are, and how to execute a block. Anything beyond that doesn't actually need to be implemented. It only needs to be implemented if you're going to use some of our pre-baked modules. In our pre-baked modules, we have a metadata module that's very good for the JavaScript environment, being understanding what the chain is all about. A block builder module that helps us build blocks, surprisingly enough, and author blocks. And a tag transaction queue that helps us manage the transactions and understand the dependencies between them. And that's it. That's literally all the code that I have come to this demo with that isn't part of the general Substrate library. What I want to do is start a Substrate chain. So I'm going to start a dev chain by running node --dev. And there we are. And if things are working, it will start producing blocks. There we go. There's the first block in. And I'm going to start our Substrate UI, which should work just like that. And I'm going to open up a browser. And open. And no, we will not be reporting to Google, thank you. Here is our basic Substrate UI. You can see there's a bunch of small things. Basically, all of the little modules that the node template comes pre-configured with have their own UI component, and this is where we can interact with them. We can see that the node version is 0.9. We're on the development chain. Our runtime is template node v1, and our implementation is Substrate template node v0. We mentioned that before. The chain is currently 11 blocks long, and we have one authority. Now, first thing I need to do is add Alice, our sort of key, onto here. And to do that, I will make a new tab and use subkey, and I happen to know that the key for Alice is, the seed for Alice is Alice, so I'm just going to copy that. Oops. Copy that and pop it in here. And we'll call you Alice. So there's Alice. If we have a look at how many funds Alice has, she has quite a lot of funds because this is a testnet. We're going to give a few funds to the default. If you just want to give a few funds to the default, well, let's say we'll give 5,000 units and send those. And that will get mined onto the chain or whatever, and once it goes to a green tick, it means we're good, and as you can see, default now has 5,000 units. Next thing to do, let's hack a new runtime module. So in the runtime, we're going to create a new file. We're going to call it demo.rs. I have my cheat sheet so I don't forget. We're going to use a couple of, we're going to bring in a bit of software. First thing that we need to use for later is parity codecs encode trait. We also need our runtime modules. We need basically access to storage, which is done, support, which is done through a couple of traits, storage value. I'm sorry if you don't know Rust, I'm using this terminology. You should learn it though, it's a very good language. And end result, there we are. And we also need runtime primitives. This is to do some hashing later on, which, as you will soon find out, this demo needs. And finally, we're going to use a couple of the utilities and modules from the other runtime modules. In this case, we're going to use balances to do stuff with balances. We're going to actually require that as our trait. So all modules have this configuration trait. We just call it trait. It goes in the module at the top. And you can specify any other modules that it requires. In this case, it requires the balances module. Next, we're going to declare our module. This basically comes down to writing a structure. It's got a slightly terse format. We're going to our module is configured by this particular trait. We get when we write a module, we write a bunch of functions that get executed when particular transactions come in on the chain, and they get automatically. It's all very clever. It automatically marshaled and routed into this module. We don't have to think too hard about it. All such calls have a particular origin that tells us where the call came from. If it came from a transaction, then it's signed. And if we want to, we can sort of check who it was signed by. It's kind of like misc.sender in Ethereum. Everything has a result that it has to provide. We're going to provide. We're going to write a silly game module, right? Because these demos are always fun with a bit of gambling, and I think the Chinese like it. Sorry. So we're going to go here. Result. So decal storage. So those are our two entry points. We have one that lets us play a game, and one that lets us store some stuff between. Sorry, we have two entry points. One that lets us play a game. One that lets us set the payment. We do this first because we can't be sure that it will be initialized, because we're going to do an on-chain. Upgrade. Now, our module is going to be called demo. We're going to store two things. We're going to store how much has to be paid every time we flip a coin. We're going to do a coin flip game. Keep it simple. And how much is currently stored in the pot. The way it will work is we will pay this payment. It will get placed in the pot. We'll pay this payment. We'll flip a coin. If we get lucky, we get the contents of the pot. If not, then we don't. And finally, we will put our payment into the potentially now empty pot for the next player. So we're up to the parts that are actually interesting. So the first thing that we have to implement is the play function. This takes an origin. This is all generic, which means we can really easily write unit tests. So we're going to let the sender, we're going to require the sender, so whoever's signing this, to come in. We're going to require them to we're going to require the origin to be a signed origin, and we're going to interpret the signature and get a sender from it. This will give us an account ID. Now we're going to grab the payment and put it into a local variable with self-payment. We can just do self-payment because we introduced the getter up here. If there is no payment, if we haven't put one into the database yet, because payment is actually an option. So if it's not there, we're going to exit with a must have payment initialized. Exit with a message. Okay. So first thing we need to do is decrease the balance of our sender. So we go into the balances module and call the decrease free balance. We send it the sender and the amount that we have to decrease by, which is payment. Okay, so far so good. Next thing, we have to flip a coin. So to flip a coin, we're going to use the system modules random seed. Yeah. And we're going to combine that. We're going to stick it in a list along with the sender, or a reference to the sender. And then using that, we can use this using encoded that basically serializes it. We're going to pass it into our hash algorithm. And then using the contents of our hash, which is a cryptographic hash algorithm, we're going to take the first byte and see whether it's less than 128. Okay, so very, very simple, completely, well, somewhat gameable coin flip. Next, we're going to, if we won the coin flip, increase the free balance using this increase free balance creating API in the balances. And it'll be the balance of sender, and we'll take the value of pot. So what take does is it just reduces it to 0 and returns whatever value it was. Actually, it doesn't reduce it to 0. It removes it entirely from the database and returns the value it was. In our case, it's going to default to 0 if it's not in the database. Okay. Finally, we're going to add some payment into the pot. So as I said before, we will add payment into the potentially now empty pot, and once that's all done, we return our result, which is okay, we're good. The next thing to do is to have some sort of initialization mechanism to actually put the initial payment in, since we can't do that when we upgrade the chain yet. That is an API we're thinking of introducing there. We don't require an origin for this one. It doesn't actually, the origin's irrelevant because it's a one-off call, and we're going to check, rather than checking the origin, we're just going to make sure that it hasn't yet been set yet. So we go to self-payment and we check whether it's been set. And if it hasn't been set, then we set it to the value that we've passed it. In this case, value. And we're also going to set the pot so that whoever plays it first doesn't just get an empty pot to put money in and not win. And then finally, return OK. OK, so that's our module. that's as easy. That's all it is to actually code one of these things. And if I haven't made any typos, it should even compile. The only other thing we need to do is we need to integrate it into our runtime. So if we go in the runtime, the first thing we need to do is just introduce our module, so tell Rust that our module exists. That's pretty easy. Next thing we need to do is, well, we're introducing a new version of the blockchain, so let's rename our specification name to demo, and our impl name to, I don't know, demo node. We can leave the version numbers the same, since we've now changed the name. That won't create any issues. And then finally, we need to implement our configuration trait, so demo trait, for the runtime to let Rust know that this runtime can indeed handle this demo. Since we didn't actually have anything in the trait, that can be left empty. And then the last thing we need to do is configure it, put it into the runtime construction thing to tell, again, Rust about the module. And we haven't implemented some of the default things like events, so we're just going to do that. We have to spell out which of the components we have implemented. Okay, let's try compiling that. It's these live coding exercises, they're a lot harder on compiled languages. I really hope I haven't made any typos because it might be a pain to make it work. But anyway, let's try. We have a script that builds the WebAssembly called build.sh. Traits. No, that should be trait. Try again. Impl trait. I probably forgot to put the module. Yep. Did you notice any other errors? Yes, a semicolon is missing here. Okay, so that's now built our new module. Let's try and upgrade our chain. So that's now a whole new, different chain that has this whole new piece of functionality in principle, native code. It's no, it's good. So we're going to go into substrate node template, and in the runtime, in the WASM, because we're giving it a WASM blob, we'll have found a new, oh dear, we'll have found a new thing compiled, I hope. Node runtime.wasm. There it is. Oh, node runtime compact.wasm. That's even smaller. Let's use that. And there we go. So we've given it to our little runtime upgrade thing. All this does is it goes into the runtime upgrade module and says, please upgrade, please set the code to this new code. There's really nothing to it. If you're interested in the workshop later, I can show you. And we hit the upgrade button. So that's sent the transaction to the chain. And if all works, we should see this switch, there we go, to our demo chain. So this is now a completely different blockchain with a completely different code at its heart. It's a bit of a pain to work with, but I can show you exactly how much of a pain, because we still need to call that initialization function to make stuff work, the set payment thing that we did. So let's open up a console. Now, there are a few interesting objects that we get in order to interact with our modules. They allow us, they're built on, well, we actually have several JavaScript libraries that we use. One of them is built on the Bonds library that I did last year. That's the one I'm going to be using now. There are others if you don't like it. We have a runtime object that tells us all of the modules in the runtime, and if I list this, then we will see that the modules now include the demo module. They didn't before. And a calls thing, which lets us actually interact with calls. So if I want to make a demo call with set payment, then let's say we want to set payment to be 1,000 units. then that's all it does. It's as simple as that. If I want to make a transaction, then it's as simple as writing post the sender. So who's the sender? For the sender, we're going to use the runtime balances. We're going to decode an address, so we're going to use the runtime balances SS58 decode, and I happen to know Alice's address is this one, so I'm going to use that. It's nice and small. That's because we have address indexing, and I'm going to call set payment 1,000, and that's going to be from Alice. Oh, sorry. Can I do this? Okay. Okay. You can all see that. I'm going to tie that to console log. What that means is that as the transaction goes through, it will give us updates on the console. So it's been sent to the chain. It's now ready for mining, and there we go, finalized. Now I can see. Let's ask the runtime what's in the pot. This looks a bit like a promise. It's not. It's a bond, but it does more or less the same thing. And there we go. 1,000 is in the pot. So it's been initialized. Let's now. I want to show you for the last part of this. Let's add a folder to the workspace. We're going to add the UI folder, and I'm going to go into the source and go into the app. I'm going to add a new segment to this UI. So we're just going to copy and paste this because it's a lot similar. We're going to call it game, play the game. Play the game here. And we will file upload bond, content select runtime. So we've got, we don't need a file upload bond since we're not uploading any files. We do need whoever it is that will be playing the game to be in there. So we're going to use an account ID bond. Let's just copy and paste that. And we'll pop it in here. And rather than this dot destination, it's going to be this dot player. And other than that, it should be about right. Player. And the transact button won't be upgrade, but it'll be play. We don't really need a warning. We'll just put a game on it. The sender will be our player. So it's just this dot player, which we'll add in a second. And the call will be calls.demo.play. And it doesn't need a parameter. The only other thing we need to do is add our new bond. Save that, load it up here, and there's our new play the game module. So let's play the game. We've given default a bunch of tokens, 5,000. So we just hit play, and the transaction will be sent, and we'll soon find out. No. So they lost that one. It cost them 1,000, and there was a transaction fee of 1 unit. So they're now down to 3,999. If we have a look to see what's in the pot, let's just check the pot. And indeed, the pot's gone up by 1,000 units. Let's see if they win in the second play. Yes, they did. So they've gone up by 2,000. Of course, the one dot transaction fee. And this one isn't on my notes, but let's see how hard it is to put in a label of the current pot's balance. We'll just copy this label and pop it maybe after the transaction button. And we'll say, instead of balance, pot balance, we'll go into here, but rather than it being the balances of our player, it will be the runtime demo pot. It's as simple as that. Let's go over. Oh, pot is not a... no, I don't need the brackets. Go over there. And there is the pot balance, 1,000 units. And if we carry on playing the game, we'll see it either go up or go down. And that is as simple as it is to create a new runtime module with a UI in Substrate.